Okay, now that we understand some tools for assessing a simple linear regression model, let's apply them. Let's come back to Google Sheets and apply those techniques to the model that we discovered, namely this equation here, right? Which was computed using the data we have here, okay, and the scatter plot here, okay? So the output is going to give us the values for the coefficient of determination, r squared, and you can almost see it yourself. Here it is, r squared. Now there are other ones that look similar, adjusted. We're not talking about that here. We're talking about r squared. So what is that r squared telling us? Well, first off, it's 0.5808. If we round it to about 3 decimal places and convert it to a percentage, we can interpret what this means. So we've talked about this in general. Let's apply it. So 0.58 to 3 decimal places and then convert it to a percentage becomes 58.1% of the variability in house price is explained by our simple linear regression equation. And when I say by our simple linear regression equation, I am talking about this guy that we got in the very first step after we used Excel Miner, where we pulled the coefficients out and we put them all together in the form of the equation. Y hat equals B0 plus B1 times X, right? So it turns out that by 58.1% of the variability in house prices, so obviously just take a look at house price alone. Obviously there's variability in house prices, even in this one neighborhood. So by knowing the square footage of the houses, right, by having this extra piece of information about each house, we are 58.1% better off at predicting how much the house is going to sell for, the price of the house, than if we didn't have this column, this extra information. And the only information we had was the previous house prices. Okay, that's another way to think of r squared. Okay, by the way, we represented it like this, right? So we know also that r squared is equal to the correlation coefficient squared, so we could try and see that we get the same value. And in fact we do. So look at this. Isn't that r squared? I just squared r. Okay? So that's r squared. Now, how about the other assessment tool we have, the model utility test? So remember, HO for that test was that beta 1 is equal to 0. Beta 1, remember, was the true slope of the population regression line. In other words, if we had all the house prices and all the square footages of all the houses in this neighborhood that we're studying that ever were sold, that would be the population data. We clearly don't have that. But if we did, and we ran this same exact method that we've done so far, the coefficients that we got would be the true coefficients. So we used the betas to indicate those. Beta 0 for the true intercept and beta 1 for the true slope. Since what we got are sample estimates of these guys, we give them the Roman letters B0 and B1. So the null hypothesis here is testing whether the true slope is different than is equal to 0 versus the true slope is not equal to 0. Okay, now let's just think what these mean in words. If the slope of a line is 0, that pretty much says that as x changes, nothing happens to y, right? It's just a flat line. That would be the case if you had a null plot. Remember those scatter plots where we looked at in one of the earlier videos in this module, where the points didn't really have a clear pattern up or down. They were pretty flat. So we would summarize this with a flat line. What's the slope of this line? Well, the slope of this line is 0. So when you say beta 1 equals 0, you're saying that the true slope is equal to 0. You're saying that there's no meaningful linear relationship between x and y. Okay? Now, we're applying this question to our data in this real estate example. The alternative hypothesis says that the true slope is not equal to 0. So not equal to 0 means that there is some meaningful or significant linear relationship between x and y. If we apply it to this question, we're saying that there is some meaningful linear relationship between the square footage of a house and the price it sells for. So, in words, the null hypothesis says there's no significant linear relationship between x and y. The alternative says there is some significant linear relationship between x and y, just not equal to 0. So it could be a negative relationship, it could be a positive relationship. We don't care. We're just testing whether there is some meaningful or significant relationship, linear relationship. Okay? So let's apply that to our example. We'll use an alpha of 5%, pretty standard, to make our decision. And so we go over to the row where B1 is on. B1, remember, is an estimate of beta 1. Okay? So we're going to use the estimate of beta 1 to make a statistical decision on B1. So we go over, we already know what this guy is. This is the coefficient. We keep going over and we hit a p-value. There it is, p-value. Remember, we use p-values to make decisions on hypothesis tests. So the p-value for this test is given here. Okay, so it's getting all scribbly scrabbly here. So there's the p-value. So I compare this p-value to alpha, and if it's less than alpha, remember, I reject HO. So let me just write this again. HO was that the true slope is equal to 0. There's no significant linear relationship between square footage and house price. And the alternative hypothesis says that there is some, be it positive or negative, linear relationship between house price and square footage. I told you to use alpha of 5%, and we look at the p-value on the row for the slope, not the other row, the intercept slope, and we see that it is indeed less than alpha, so we reject HO. So the p-value method for making statistical hypothesis test decisions is always the same. If the p-value is less than the alpha, then less than the level of significance, you reject the null hypothesis. So we reject HO here, and we conclude that there is some useful linear relationship between x and y. So let me put that in words. Model utility test for this data indicates that there is evidence, or let's just say there is a significant linear relationship between, I don't want to say x and y, I want to use the variables in question, between square footage or square feet and house price. Okay, that's always good to see if you want your model to be a good model. You want to reject the null hypothesis for this hypothesis test that we were just doing. Okay, so that's a good sign. So I mean, it's beyond your control, but it's a good sign when you reject HO for the model utility test. It tells you that the model is a good model. It's doing a good job. Okay. Now let's go back to R square and see how both of these together are telling us about how well our model is performing. 58.1% is not the greatest R square, but you can't really say that's a low or high R square without explaining the context of the study being performed. If this study is about something that's highly variable, like real estate house prices, then 58.1% might be a very good R square. If you're studying some machinery that doesn't have much variability, 58.1% might not be a good R square. So it's based on the content of the study. And unless you're a subject matter expert in a particular field, like a real estate expert, we're not in a position to say too much more about whether that R square is good or not. Okay? So we'll just interpret it as is objectively, as we did here. Okay? Obviously, an R square closer to 1 or 100% is telling us that our model is doing a much better job at predicting the dependent variable. And if it's closer to 0, it's telling us that it's doing a poor job. So we're kind of right in the middle here, but we can interpret it objectively and leave it at that. Okay? By the way, I highlighted this earlier, observations. Well, that's just n, right? Okay? So we've assessed our model. So we went from the beginning. Let's just recap. We had data. We had an objective. We were a real estate broker, and we wanted to predict house prices using how many square feet a house has. We start to learn about this relationship by making a scatter plot. Scatter plot shows us in this case that there is a positive linear relationship, moderate to strong. Okay, so we move on and calculate the correlation coefficient. That also tells us that there's a positive, moderate to strong linear relationship between these two variables. So now we're kind of excited, and we see that there's something interesting to tap into and learn more about. So we decide to use a simple linear regression to actually put this relationship into an explicit form, into the form of an equation. So we used Excel Miner, right? And we let Google Sheets and Excel Miner do all the calculations for us, and we get the summary output and the ANOVA output. Okay. In the summary output, we'll come back to that. In the first thing we looked at in the output was the coefficients. We pulled them out and we put them all together in the form of the equation. Y hat equals B0 plus B1 times X. We replaced all of these guys with the appropriate numbers for the coefficients and names for the variables based on this problem, and we ended up with this guy down here, the bold one. Price hat, predicted price, in other words, equals blah 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 plus blah 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 times square footage. Then we said, hey, before we start using this model to make predictions, let's assess it, let's judge it, let's see how well it's performing. So we looked at R square, and we interpreted it, and we performed the model utility test using the correct p-value on the row where B1 was. Both of these gave us an idea that our model is doing a decent job. Okay, so now we're a little more confident to actually get to the final phase where we want to now use our model to make predictions about new houses that are coming on the market. And this is very simple. So let's go back to the scenario. Let's say a new house comes on the market. So this house is 1,650 square feet. Okay, now is it within the range of the houses that we've studied? Yeah, the smallest house was 1,100 square feet, and the largest house was 2,450. So 1,650 is in that range. So we're fine making predictions about houses within the range of our X variable. I wouldn't use this model to try to make a prediction for a mansion, a 9,000 square foot mansion, because I have no data on houses comparable to this one. So I don't know how they behave. They might behave quite differently than these houses. So I'm not in a position to make predictions here. Although I could plug this number in and I'll get an answer, it's not a good idea. So I will limit my predictions to houses that have are within the range of the houses that square feet of the houses that I've looked at. So let's just do 2 houses here. Let me pick another one. Hey, a person has come to me with a house that is 2,100 square feet. I need to come up with a predicted selling price for both of these houses as a broker. So I could just kind of go based on the past. I could go kind of without much sophistication. I could go based on kind of my gut feeling, a qualitative judgment, or I could use the equation that I learned, which is an explicit representation of the relationship between the square footage and the price. So I plug in 1650 into this equation right here, and out will come the predicted house price. So let's do this. Equals, I can just click on this guy plus this guy times this guy. And all I did was, instead of manually typing something like equals 98.2483 blah 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 plus 0.10976. The more decimal places I use, the better, but you will get tired of writing 15 decimal places, times 1650. That's the square footage I want, and I get 279.35. Compare that to 279.36 because I used references instead of typing out, so I got all those decimal places here. So a house that's 1,650 square feet is predicted to sell for about 280,000. To be more exact, 279,365, right? Because this is in thousands. Now let's do the same for a 2,100 square foot house that's just coming on the market. So equals B0. I'm just clicking on B0 plus B1 times 2,100. Enter. Obviously this house is going to sell for more, so I'm happy to see that. And I see that a 2,100 square foot house is predicted to sell for 328,761 if I cut it off, if I round there. Okay? So this was kind of the ultimate goal all along, is to get to this point where I'm making predictions. Okay? And one last thing, these 2 guys down here are not Y's, so I probably shouldn't have put them in the same column. These are Y hats. These up to here are actually Y's. These are actual prices that these houses sold for. These are houses that haven't sold yet, so the best I could do is make predictions. So I distinguish these Y's from these Y hats. Okay, and that completes our example. Alright, so I hope this was helpful. If you try to just jump forward and watch some of these videos and not do them in succession, you may have problems. You may need to go back and watch some of the earlier videos, even if you saw them. Again, everything I need you to understand about simple linear regression, scatter plots, and correlation are covered in this series of videos. So it's up to you to watch them enough to get what you need out of them. Okay, to be able to answer the lab questions, the quizzes, and the exam questions. All right, so till next time, have a great day.